Hello, this is Richard Walker from Lucidate. Welcome to this video series on AI and machine learning techniques. In this series, we're going to analyse several AI techniques. We'll apply them to a couple of financial datasets. One will be a loan default dataset. We'll build models to predict which prospective borrowers are more likely to default. A credit officer would use this information to approve or reject the loan application, or perhaps demand more collateral from a prospective borrower. We'll also use a customer churn dataset. Here we want to predict which bank customers are most likely to churn based on their behaviour. Here account managers will target these customers with promotions to reduce the likelihood of them leaving and joining a competitor. As we will be comparing different AI techniques, it's essential to determine a set of evaluation metrics to assess which type of models perform best on which types of problems. In this video, we will discuss several evaluation metrics. We'll start with the frankly counterintuitive assertion that accuracy, at least on its own, is a very poor measure of AI performance. It can be used by unscrupulous developers of AI systems to fool people into believing that their machine learning solutions are better discriminators than they really are. We'll show how to spot this type of fraud so that you won't be misled. To do that, we'll discuss the confusion matrix. This separates out our AI system's correct assertions, the true positives and true negatives. Here, the AI is correctly classifying our records. For instance, for a loan default predictor, a correct classification of a defaulting borrower would be a true positive, whereas a correct classification of a repaying borrower would be a true negative. But we will also score the misclassifications, false positives, where the AI incorrectly asserts that a particular borrower will default, as well as false negatives. Here a classifier predicts that a borrower will repay when in fact they default. The confusion matrix gives us a great way to visualize the correct and incorrect classifications to get a better idea of the true performance of a system, rather than relying on accuracy alone. The confusion matrix also allows us to come up with other KPIs for machine learning. These go by the names of precision, sensitivity, and specificity. We'll describe all of these metrics and how they complement accuracy in this video. We'll see how we can combine all of these metrics to give single scores, an easy way to compare AI solutions. For military history enthusiasts, this will reprise some measures first proposed in the 1940s to analyse radar systems. So, let's begin with the perhaps surprising assertion that accuracy is at best a very poor measure of AI performance. At worst, it can be used by bad actors to mislead people into thinking that an AI solution is better than it really is. This seemingly benign and innocent equation at first glance might seem harmless and useful. The number of correct predictions divided by the total number of predictions. Accuracy has the advantage that it's very easy to define. This seems simple and neat. What could be wrong with this? As we will see, quite a lot. The core issue here is that accuracy fails to explicitly take into account false positives and false negatives. In determining a system's performance, it's more important to determine what it got wrong and the type of error, whether false positive or false negative, than what it got right. To illustrate this, let's look at a very simple loan dataset. To keep the illustration simple, we'll just look at two of the inputs. Here we have overdraft utilization on the x-axis and debt to income ratio on the y-axis. We have an output of two classifications as our target, whether a borrower defaulted, shown in red, or whether they repaid, shown in green. In this dataset, we have 7 borrowers who defaulted and 93 borrowers who actually repaid. As you can see, the defaulters typically had high overdraft utilization and high debt relative to their income. Not particularly surprising. We can use this dataset to train an AI model and get it to predict whether a borrower defaults or repays. For our predictions, we'll put a circle around each point. Red for a predicted default and green for a prediction of repay. With an unbalanced dataset such as this, it's very simple to get an accuracy score of 93%. Just predict that every loanee is going to repay. There is nothing remotely intelligent about this approach. It's merely exploiting the fact that this is a biased dataset, with most of the values belonging to one category. Presenting accuracy like this is fraud, and it gives a misleadingly high score. Beware of this. A more plausible AI classifier will get a small number of things wrong, but we'd expect to see a balance of false positives and false negatives. Let's introduce our confusion matrix to see how it can help us better describe the performance of our systems. We use a 2x2 grid. The rows represent our actual results. The top row contains all of the actual defaults. In our current loan default example, there are a total of 7 of these. The bottom row contains all the samples where the borrower repaid. Again, for our sample dataset, this will total to 93. This means that our correct classifications will lie on this diagonal. Bottom left contains the correctly classified repayers, and top right correctly classified defaulters. Our incorrect classifications will lie on this diagonal. Top left is where the AI believed a sample would repay, when in actual fact they defaulted. Bottom right are all of our classifications where the opposite occurred. The AI asserted that the sample would default when actually it repaid. In this example, we could also add some qualitative attributes to these classifications. In the top left, our model was complacent, approving a loan application that actually defaulted. On the bottom right, it was fearful, denying a loan applicant that actually went on to repay. We can use the confusion matrix to quantify key ratios and describe the performance of our model. We have a much larger sample of borrowers repaying than defaulting. For our smaller defaulting sample, we can look at the number of correctly predicted defaults relative to all defaults. This ratio is called the sensitivity. Likewise, we can look at the number of correctly predicted repayers relative to all the repayers, and this is called the specificity. Our columns in the confusion matrix show us our predictions. We can derive the model's precision, and this is the ratio of the correct positive predictions relative to all positive predictions. Use of all these metrics helps us to put the accuracy metric in better context. It's not that we shouldn't use accuracy, but we should use the accuracy in context of the other metrics and KPIs derived from the confusion matrix. Let's use an example to further illustrate this. If we start with our dubious classifier that simply classified everything as a non-defaulter, then we have the following confusion matrix. Our accuracy is an impressive 93%, but as soon as we start looking at our precision, which is indeterminate, as we have a divide by 0, and our sensitivity, which is 0%, then the shine somewhat falls off our accuracy number. If we instead look at a more plausible example that correctly predicts 5 of the 7 defaulted loans, as well as 87 of the 93 repaid loans, we get this picture. Note that the accuracy is not as high, it's only 92%, but this is bolstered by a sensitivity score of 71.4%, as 5 of our total of 7 defaulted loans have been correctly predicted, as well as a precision of 45.4%, reflecting the fact that 5 of our 11 predicted defaults were correct. We can also use our confusion matrix to help calibrate our model to achieve optimum results. Our test data's target record is the defaulted flag. This will be 1 if the borrower defaulted and 0 if this borrower repaid. The output of our trained model will never exactly be 1 or 0. It will take on a continuous range of values, reflecting the likelihood of default. The higher the number output by a classifier, the more likely a default. So where should we set our threshold to separate our predictions into defaulters and repayers? An obvious, maybe intuitive answer is 0.5. Anything above 0.5 will be classified as a defaulter, and below 0.5, a borrower who will repay. While maybe not a bad start, it's unlikely to be the optimum threshold value. Let's see why. Here we see 25 examples used to test our AI system. The borrowers that actually defaulted are shown in red, and the repayers are shown in green. The position of the coloured dot on the x-axis represents the score assigned by the AI system to this borrower. The higher the score, the more confident the AI system is that the borrower will default and that the loan should not be approved. We're interested in the AI's predictions. These can be assigned to the 4 quadrants of our confusion matrix. If we set our threshold to 0.5, then every score below 0.5 will be predicted to repay, and we'll circle these in green. And every score above 0.5 will be predicted to default, circled in red. This will result in the following confusion matrix. We have no false negatives at all, and we correctly find all the defaulters, our true positives. Our model is very sensitive to finding all the defaulting loans, and it gets a great sensitivity score to reflect this. However, we incorrectly assign 9 borrowers to the defaulters category, and with 9 false positives, both our precision and specificity scores suffer. Our accuracy is 64%. So, is 0.5 the best threshold? Let's push our threshold up to 0.8. Here, we only correctly assign 1 defaulter. If we used this threshold on this model for loan approval, then we would make 4 loans to borrowers who would not pay back. Perhaps this is not ideal. Note again here that our accuracy score has increased from 64% to 75%. Yet this doesn't seem as good a model as having the threshold at 0.5. So if we lower the threshold to 0.545, we get a more balanced result. At this threshold, we have no false negatives. We aren't making loans to borrowers that will default. And here we have only 8 false positives. This means better precision and specificity scores than when the threshold is at 0.5. A great compromise for this model would seem to be a threshold of 0.63. While we misclassify 1 defaulter, we only misclassify 4 repayers. This is reflected with high scores across all of our KPIs. So, is 0.63 the best threshold for this model? Well, it depends. There are business factors to consider. If these loans are fully collateralized with high quality assets that can be assigned to the lender in the event of a default, if loan arrangement fees are high and interest rates are high, then you might tolerate an even higher threshold. For sure, we will approve loans that will default, but our downside risk is mitigated with the collateral, and we're compensated for our lending risk with a quality revenue stream. On the other hand, with low interest payments, zero loan arrangement fees, and uncollateralized loans, then we would be wise to set our threshold lower. This boils down to a precision sensitivity trade-off. If you recall how the ratios are constructed, you can either have a high precision or a high sensitivity, but not both. Given your business case, that is to say your collateral terms, loan arrangement fees, interest payments, you can use the precision sensitivity curve to determine your optimum threshold. You can also use these metrics to compare alternative models. As you want to maximize both precision and sensitivity, then you'd always favor the model with the green curve over a model with the red curve. Precision and sensitivity are often combined to produce a single metric. Here we write out the equations for our sensitivity, specificity, and precision scores. To maximize sensitivity, we want to minimize false negatives. To maximize precision, we want to minimize false positives. The F1 score is a combination of the two. Actually, it's the harmonic mean, which is twice the product divided by the sum of the precision and sensitivity. The F1 score is a very useful heuristic to compare different models. Perhaps the most widely used measure for comparing AI models has its origins in the early uses of radar in the Second World War. At its heart, a radar is a classifier used to detect enemy aircraft or ships. True positives are an incoming sortie of enemy aircraft. True negatives are when the sky is clear. False positives might be brought about by a flock of seabirds. False negatives are a failure to detect an incoming aircraft. Air Command needed to set their thresholds correctly, and to do so used ROC curves. ROC stands for Receiver Operator Characteristic. The setting of the threshold involved the tuning of the radar receiver by the operator. The classic ROC curve plots the true positive rate versus the false positive rate. The true positive rate is what we've been calling sensitivity, and the false positive rate is 1 minus the specificity. What you want is a threshold that gives you a high true positive rate, whilst at the same time giving you a low false positive rate. By plotting this curve, you can choose a threshold value to achieve this. Just as important is you can use these curves to compare different models. The area under the ROC curve, usually abbreviated to ROC-AUC, can be found for each model. In the example on the screen, the model with the blue ROC curve is superior to the one with the red ROC curve, while the model with the yellow curve is the best of all. This is Richard Walker from Lucidate. Many thanks for watching this first video on machine learning. In this episode, we've looked at KPIs for our AI and machine learning models. We've seen how accuracy is perhaps a misleading metric for evaluating AI performance, particularly when used on its own. We've seen how to use a confusion matrix to derive additional KPIs such as precision and sensitivity, and see how they're a better way to describe how effective our classifiers are. We've seen how to use these measures to optimize our models, and how we can further derive measurements such as F1 score and the area under our ROC curve to provide superior metrics to accuracy alone. Please join me for more videos in this series where we describe, evaluate and compare different machine learning models for our loan default and customer churn data.